I think we're good. Yes. All right. Other than the exams not being back, everyone doing all right? Surviving the win? Cool. So we left off after the exam with this. Marked up something called completing the square. So just to remind us, get us back in the mindset. So this is a technique, an algebraic technique used to literally complete a square if we model, I guess, 12x squared, x squared plus 12x with an area approach. And one thing I just want to show really quickly. Maybe not. Okay, you know what? I think I'll just do it here. No, that's going to be too tedious. So this is working. So the website is called Mathigon, and kind of a lot of cool math things on here, which is not showing up, sadly. Just was. There it is. So one of the things we can do is just kind of look at, as I was showing before, a little, I guess, clearer concrete model of x squared geometrically. So we know x squared algebraically is x squared, but geometrically it's literally a square. We can say its dimensions are x by x, so therefore its area is x squared. And then something like, I don't really feel like dragging 12 of these, but I can do 4 of them. Maybe I'll do 6 pretty easily. 4, 5, 6. So now we have more area. So we have x squared and a total of 6 more x's. So what we're really looking at is a geometrical model of x squared plus 6x. Each one of these, well, it's the same row, x, therefore each value right here has to be a 1. So that we get the inside area of x. So as we were kind of setting up last time, row x, column 1 would give us an area of just x, and so on, and so on, and so on, and so on, and so on. And so there we go. There's our area model of x squared plus 6x. In a way, it directly shows factoring. So it says x squared plus 6x. We know how to factor that. Factor out the GCF is x times x plus 6, which we exactly see right here. Row x, boom, column x, plus 1, plus 1, plus 1, plus 1, plus 1 would be plus 6. So rows and columns. So again, algebra, pretty simple, just a geometrical approach there. Furthermore, to really emphasize, oops, that's not what I want. Where's the eraser? To emphasize completing the square, we can take 3 of these as such, rotate them as follows, never change the area. But we can now see we have x by x, 1, 2, 3, 1, 2, 3 that way, and definitely an incomplete square, which 9 of these bad boys will fit very perfectly inside to complete the square. So satisfying. One thing to notice that's going to be brought up in just a few more minutes, I no longer have the same area because I've added something to it. I've changed this quantity. So it was x squared plus 6. To complete the square, one must change the value and add 9. So now that's a new expression. So it's not the same value as it was before. 9 would complete the square. And I guess just to keep it formal. There we go. X squared plus 6x plus 9 arranges perfectly as a squared. Furthermore, just get rid of this. We can say this expression, just like the factored form, we can write this in its factored form as, and I'll just put a 3 there and a 3 there, as x plus 3 squared. Boom, there we go. And this arguably is a helpful form, so reminding us transformations and the x squared graph, which is a parabola. This now we can say, hey, I don't know much about the parabola in that standard form, but in this form, now I know it has a vertex shifted 3 units to the left and no units upwards. So this is just a transformation of x squared. And so that really kind of sums up completing the square. One value of it is to be able to gain some information from this. It has other value later in different areas of math. But for now, we move onwards. So the goal tonight is to look at, not this again. There should just be a button to switch this. But one more. Now I can't get. Now it's not switching over. Come on. Behave. All right. Yes, business. All right. So now tonight what we're going to do, look at a few things. First, solving quadratic equations by completing the square. That will then lead to taking standard form and writing it in vertex form. So we should recognize this as transformation. We'll talk about a shortcut to come, the good old quadratic formula from algebra. Do a little bit of graphing and a bunch of applications with quadratics. So that's our goal tonight. Solving equations with completing the square, looking at standard form and be able to find key features of quadratics by completing the square, look at a shortcut for that, and then some applications which uses the quadratic formula and a bunch of stuff. So we got a pretty busy night. Off we go. Solving quadratic equations by completing the square. Number 1. So when you have an equation, remember we're allowed to do things to both sides. So the idea is to complete the square. So if it helps to draw a visual, you can. The one thing I like about the visual, and I asked you to watch Mr. or Dr. James Tannen himself describe the power of completing squares. It almost gets burned in your brain. So if you can do this without a picture, good for you too. You don't have to show this, but as a reminder, we know x squared is going to go there. We're going to take the 6x, divide it into 2 equal parts, which means we're going to get 3 and 3. And 9 completes the square. So roughly 5 minutes ago, I said, hey, look, we just changed the value. That's no longer x squared plus 6x. I literally just added 9. So to make this a completed square, we add 9. But since it's the equation, we can do that to both sides. So we must add 9 to both sides. Next, we write the left-hand side in its factored form. So we have x plus 3 by x plus 3 rows, which means we can write this as x plus 3 squared. The left-hand side can be rewritten. That's why I showed those algebra tiles again pretty quickly. This is like the area inside. Now this is the area written as rows by columns. On the right-hand side, we get 16. And now we can solve this equation by inverse operations, by undoing. We can undo squaring by what? What allows us to undo squaring? Square root. So take a square root. If anyone ever asks you, it's called the square root property. You're allowed to do that to both sides. And we must include a plus and minus symbol. So that's really what I want to emphasize here. Square root property, pretty straightforward. You want to undo squaring, take square root, but it really says you gain both plus and minus. I'll show you that at the end of this. Yeah. Just, what do you mean by that? Like it's on the plus or minus 16. Yeah. On the right side. So it wouldn't be on the left side? Nope. On the left side, we have x plus 3 squared, then square root. Well, that cancels out. We're just left with x plus 3. On the right-hand side, you can use a good old trusty calculator, but hopefully I've chosen an example pretty simple. The square root of 16 is 4. Last thing to do is subtract 3 on both sides. And notice how I structured that. I put the negative 3 in front of the plus and minus 4. It's just pretty standard to do that across mathematics. And furthermore, we can combine the two numbers. Negative 3 plus 4 would make 1. And then negative 3 minus 4 would make negative 7. And we've now just solved this equation by completing the square. Since it's our first example, I'll take a moment and check that it works. Subbing in 1 for x, the left-hand side makes 7. The right-hand side is 7. That's called a solution. Subbing in negative 7, this makes 49 minus 42. 49, remove 42. Left-hand side makes 7. The right-hand side is 7. And those are your two solutions. No other solutions, no other numbers work. And we're done. All right. Let's do it again over here. Really just reminding us that we can split odd numbers in half. Had that discussion at some point last class. Just call this 5/2 x. Let me rephrase that, negative 5/2 x. And we can quickly check if you add negative 5/2 and another negative 5/2, you have negative 10/2, which is negative 5. Cool. So it's as simple as just put over 2. And that reminds us this is going to be x with a minus 5 there, minus 5/2 there, and there. And I'm purposely avoiding decimals because it's actually easy to work with fractions. Negative times negative is going to be positive. 5 times 5 is 25. And 2 times 2 is 4. And you had some practice of that, hopefully, before you came into class. Just finding values that complete the square in your homework. Pretty painless. So 25/4 is what completes the square. I'm afraid to switch over to the camera, but I'll give it one shot again. Here, please work for us. Okay. So did recommend this calculator for a variety of reasons. One being, hey, you need to add 14 plus 25 fourths. There's a beautiful little fraction button right here. Boom. And if you have a calculator, I'm happy to look at it after class to see if your calculator has a fraction button. Not all do, but pretty painless. We get 81 fourths. And the left-hand side, we are going to write in its factored form as x minus 5 halves squared. From there, everything is going to tumble into place. Take a square root with the square root property. Left-hand side's pretty painless. And actually, in this particular example, the right-hand side isn't too bad either. 9 halves will do the trick. We can quickly check that. 9 times 9 is 81. 2 times 2 is 4. So 9 halves times 9 halves is 81 fourths. So therefore, the square root of 81 fourths is 9 halves. Add 5 halves to both sides. Again, pay attention to how I structured that. And we can add and subtract. So 5 halves plus 9 halves. Hey, they have common denominators. If not, I probably just use my calculator anyways. But that's going to make 14 halves, which simplifies to 7. And then 5 halves remove 9 halves is negative 4 halves, which makes negative 2. Our two solutions. So once more, just give it a little quick check. 49 minus 35. 49 take away 30 is 39. Take away is 19. I'm sorry. Take away 5 more would be 14. And then negative 2 squared becomes 4. Negative 5 times negative 2 is 10. 4 and 10 make your 14. So two solutions, once again, work out pretty nicely. Onwards we go. Oh, wait a minute. I went a little quick there. That's all right. So fundamentally, what's different in this example than the first two? Notice we have a value. We have a constant value of 3. Unlike in the first two examples, I just had my x squared and my 6x. Example 2, x squared minus 5x. So I can fix that. What I'm trying to argue here is that I know how to do it when there's just these two things. This 3 is kind of distracting me, so why don't I just get rid of it off the bat? So now it's x squared minus 2x equals 5. Not going to change how I completed the square, so I still need to add 1 to both sides. Write this in its factored form. Call that 6. Take a square root. And we have x minus 1 equals plus and minus root 6. 6 is not a perfect square. 2 times 2, 4 is a perfect square. 3 times 3, 9 is a perfect square. So we went from 4 to 9, and we missed 6. So just a brief reminder, if you needed to know more about what the square root of 6 is, turn to a calculator, which I'm doing right now, and find that it has a decimal approximation of about 2.449489743. Don't need to know that. It's on a calculator. And actually, don't turn that to a decimal. We just keep this in what we call its exact form. It's a fine number, maybe not applicable, but in math class, it's a fine-looking number. It's the square root of 6, so leave it alone. Simply add 1 to both sides. And those are your 2 numbers. Those are your 2 solutions, 1 plus the square root of 6 and 1 minus the square root of 6. In your homework, at least one question, if not more, will say, solve, give the exact solution. If you change that to a decimal, don't send me an email and say it's marking it wrong, because a decimal is not an exact answer. Those are your 2 exact answers. 1 plus the square root of 6 and 1 minus the square root of 6. In at least one question, it will say to give the approximate solution to 4 decimal spots. So turn to a calculator. 1 plus the square root of 6 is about 3 point, and I know it asks for 4 decimal spots, so 4495 after you do some rounding. This is called an approximate solution. 1 minus the square root of 6 is about 1 minus the square root of 6. Negative 1.4495. And so I call those the approximate solutions. They'll get you really close. What I'm not going to do, because I can't do it in my brain and it's just not worth showing on a calculator, but if you're curious, if you were to actually take these approximate values and put them in, you're not going to exactly make 8. You're going to get really, really close. Like I'm guessing here 7.999 something, but not exactly 8. If you wanted to get exactly 8, then you need to use the exact form. So that's the difference in different sciences and math. You can use whatever level of decimals needed. I know I saw something about NASA saying, it was Bill Gates saying that they could put people on the moon with 6 decimal spots. So after 6, I'm not sure what level of accuracy is really important, but if you go into any engineering, you'll figure that out. So protect our bridges and everything, maybe you need 10 decimal spots. So you would just turn to the exact form to get that. All right. One more example where we definitely have a fundamental difference. We have a negative 2x squared in front. So looking back at the picture, thus far tonight, all the examples, even this last one, had 1x squared. And that's important because we want to complete a square. And don't write this down, but for instance, it wouldn't be illegal to say this. All right, I have negative 2x squared here, but what the heck do we put outside here? Well, x times x gets us close, but what times itself is going to make a negative 2? That's called a complex number. It opens up way too much ugliness, which we won't attack because there's a much simpler approach, which is simply to do what? What do you think we're going to do? Factor it out. Exactly. Even the next step after factoring out is just dividing everything by -2. Right. So we can divide everything by -2. And that'll take care of our issue. Now this has vibes similar to the previous question, meaning things are looking better. I got 1x squared, but I still got this +9 constant term, so we'll kick it over to the other side. And as I am wrapping this up, I've said it a few times tonight, the picture helps. Do what's helpful. The picture helps me, and I have a master's degree, so I have no shame in showing it. If you can do it in your head, awesome. That's fine too. X times X, we're going to split the middle. Call this -3, -3. So I'm adding 9 to both sides. Write it in its factored form. And we get -2. Yeah.
Is this 0 divided by -2 equal -2?
No. Scary. I was scaring myself for a minute. I was like, I don't see where this is going, but okay. All right. 0 subtract 9 would be -9, and then we're adding 9 to both sides. Okay, that's making me a little more relieved because I didn't think I put where that was leading on here just yet. Okay, so thank you for calling me out on that. Take the square root of both sides using the square root property. Boom, boom. We're going to get, actually, what are we going to get on the right-hand side? What's the square root of 0? 0. And is there such thing as positive -0? No, there's just 0. So here, we're just going to get one solution. We're just going to say x minus 3 is 0, which therefore, adding 3 to both sides, x is 3. And we're done. Yay, completing the square, right? So hopefully this is recording. Bought a little microphone. Audio should be good from now on. I gave it a lot of tests. The strategy is as follows. When you go back and restate this in your own words or watch the video, you want 1x squared. We don't care about this. It could be 6, it can be odd, it can be negative, it can be anything, right? It's odd, but we definitely want our bx. I'm just going to say b stands for some number times x. So 1x squared and some number times x on the left-hand side. If, like in example 3, you have a constant, move it to the other side. If, like in example 4, you have a constant and something else besides 1x squared, first divide to make it 1, and then kick the constant over, right? Other than that, use the visual approach, or not, but solve by completing the square, take a square root. If you have numbers like square root of 6 or square root of 11 or square root of 15, non-perfect squares, leave them in their exact form. Pay attention to the instructions in the homework. If it does ask for an exact value, you simply put 1 plus square root of 6, comma, 1 minus square root of 6. Those are your two exact answers. If it does then ask you at some other point to round to 4 decimal places, turn to a calculator. And it is potential that you can get just one solution. So a little bit of everything in those 4 examples. Next, so not last time we were here because we took the exam and introduced completing the square, but before that, so I want to say a week ago, I talked about the 3 forms of quadratic functions. So you might need to go back in your notes and review that. And they were standard form, ax squared plus bx plus c, They were vertex form, which looks like this. And then there was intercept form, which we'll talk about not tonight, another day. Right? Today, in this particular example, we're going to specifically talk about standard form as well as vertex form. And right now, converting from standard to vertex. A question you might be asked, find the vertex, the axis of symmetry, and the extreme value. So I bolded that because extreme value stands for either the maximum or minimum output. Keep that in mind. We're going to find the biggest or smallest y coordinate in just a few moments. All right, so with no further ado, how do we do that? Well, it fits nicely in this conversation of completing the square. Right? There will be a shortcut to this, though. But for right now, first, let's just call this y. Just to make function notation a little more easy to work with. You'll see what I mean in just a minute, okay? So all I've done is a very easy step, call f of x y. Just instead of that notation, call it y. And now we're going to complete the square with the quadratic expression. So like equations, we're going to kick that minus 14 to the other side. We are ready to complete the square. So good old 16 will do the trick. I want to add 16 to both sides of the equation. So y minus 14 plus 16 equals x squared plus 8x plus 16. Clean up what we can. On the left, we get y plus 2. And we factor, which you don't have to go super crazy. It's right here. Rows by columns. X plus 4 squared. One last step is to subtract 2. And then put it back in its fancy notation. And now we have completed the square to take standard form and legally change it into what we can't see right now, what we call vertex form. As I said before, it's really like the transformations from our previous kind of unit. So you can recognize there's an a value of invisible 1. We know this is going to move it left 4. And this down 2. When I say it, I'm talking about the entire parabola, which is a shape you need to know really well for this course, and if you're taking calculus and beyond. So x squared is a parabola, just reminding us 0, 0 is the vertex. This is a transformation. There's no vertical stretch or shrink or reflections, but there is a shift left 4 and down 2. Hence the name vertex form. We can clearly see the vertex in this structure. -4, -2 is your vertex. Another thing we were asked to find is called the axis of symmetry. So again, I believe a week ago, briefly talked about the axis of symmetry. I'll draw it over here, but I'm going to end up erasing it. So it's this invisible line that if we folded the parabola, if we could just fold a parabola on to itself, that would be the crease line, right? And it's a fancy name called axis of symmetry, which I just will abbreviate AOS. One major thing about that, to get it marked correctly, it must be written as an equation. And the equation is x equals whatever the x coordinate is of your vertex. So the axis of symmetry passes through the vertex. It's a vertical line. I'm not putting you on the spot, but in college algebra or any algebra, you were told, hopefully, that the equation of a vertical line has the form x equals whatever number, whatever point passes through, like a point on that line. So we do have a point on that line. X is -4. So just really want to emphasize, to get that correct, you have to put the equation x equals. If you just type in -4, don't send me an email. I'm going to say, nope, watch the video, pay better attention in class. Last but not least, the extreme value. Well, I guess I should have kept that parabola on the screen for a minute. So I'll put it back with a little more detail. So again, x squared looks like this, but we know it's shifted left 4 and down 2. So something like this. To here. Other than that, no other change, no other transformation. So we're going to say that this parabola opens up. That's how we're going to call that. That's an opening up parabola. Literally points to the sky. And when you have a parabola that opens up, this turning point, this vertex, is your smallest y coordinate. Again, nothing you really need to write here, just really digest it, because these y coordinates are higher. These are higher, these are higher, these are higher, these. This is your smallest y coordinate. Putting it all together. If your parabola opens upwards, we say -2, in this particular example, is the minimum value. And that answers what we were asked to answer for this question, right? So a few things there. Completing the square gets us to vertex form. Change f of x to y, subtract your constant, complete the square, add the number to both sides, just put it back in its fancy form. Recognize that's called vertex form, which is just very nice name for transformation form. But from it, we can quickly identify the vertex, -4, -2, left 4, down 2. Your axis of symmetry passes through the x. And I guess this might be a nice little color here. If I say that your extreme value comes from your y. What's up?
On the homework we put in for the minimum or maximum -2 there, that would be correct. We don't have to write it as a y equals.
Correct. It's just a number value. A lot of little crazy nuances, but absolutely for sure, equation, this is just a number.
Isn't that just because like x equals -4 is that line?
Yeah, it's literally an equation. Like if we were going to, and I was going to, but I'm not going to tinker too much. But if, fine. I always say I'm not, and then I do. So always that. But just to do it, why not? Give you a little mental break for a minute, and to stick to the fact that whenever I say I'm not going to do something, just give it a minute, and I will do it. Yes. So we can check our work since I'm here. The standard form is x squared plus 8x plus 14. So if you really needed the answer, there's the quickest way to do it. Maybe even quicker than AI. Okay. But you can't use something like this on a test or a quiz, and it's not the purpose, right? We're learning mathematic tools and techniques, but we can still check our work. I'm going to type in its vertex form, its transformation form, and the two graphs better overlap. That would mean my work is correct, as they do. So we can see from here, standard form, equivalent vertex form, the graphs overlap. So weight off my shoulder. Secondly, or thirdly, if I just type in -2, nothing happens in any type of graphing calculator, whether you have a handheld one or even Desmos. When you type in x equals -2, you will not get the axis symmetry because it passes through -4. And now I'm all over the place. X equals -4. All right, that just keeps getting worse. X equals -4. And there you go. That's how you graph the vertical equation. And hey, just because I'm here, if you ever wanted, you don't have to. It's not going to be something to do in this class. But if you take a science class and you want to screenshot this, you can play around with the colors in there and change it so that it's a nice little symmetry line and so on. So end of story there. Lastly, the minimum value is literally just the minimum. So -2, nothing, no equation to it.
The other way of thinking it would be like, because it's the lowest output that there is.
100%. 100%.
Also, the other one you have 1
Yep. I should have emphasized that, but hopefully it's still in your mind. As I was saying before, like those y coordinates everywhere else are bigger than -2. Call this y. I am going to subtract the 2 and then divide by the -3. You could divide by the -3 first. I'm just going to subtract the 2 first. And now divide everything by -3. So I'm purposely writing the left-hand side like that. You might want to come back to this part of the video later. Right? Because ultimately, I'm going to solve back for y after I complete the square, right? So I don't have to worry too much about that side. It's kind of just reminding me at some point I need to undo the division of -3 that I'm doing right now, and I have to undo the subtracting 2 that I did just a moment ago. The right-hand side looks like what we want. 1x squared with a bx. For time's sake, although you can draw as many pictures, I'll stop saying that, but I can literally see -1, -1. So 1 is going to complete the square. So y -2 -3 plus 1 equals x squared minus 2x plus 1. The right-hand side looks like x minus 1 squared. Give a minute to catch up here. The left's pretty ugly, but it's not impossible to deal with. You'll see, not that bad. And so to get y by itself, I'm going to subtract 1, then multiply everything by -3, and then add 2. Ready? Subtract 1 on both sides. Notice how I'm structuring it. I'm keeping the form that I want. When I multiply by -3, I'm going to highlight this for a moment. This gets multiplied by -3. So we're just going to be left with y minus 2. We're going to put a -3 right in front of the group. That's going to become our a value. And then we need to multiply this term by -3 as well. All of that is important. So multiplying by -3, smack it right there. And to this term. Lastly, adding 2. And now that I think I figured this out, let's look at it, check my work. Standard form was -3x squared plus 6x plus 2. After completing the square and changing its form, we have -3 in front of an x minus 1 squared group, then plus 5. Once again, confirming my work is correct. So everything I said was important, especially that -3. Haven't taught this enough times. Students will sometimes just put it in front of the group, but forget to multiply that outside number by it. So work cautiously and carefully. It's what works. Furthermore, I'll switch back to the tablet in just a minute, but we can now see, since a is -3, thinking transformations, negative means the original parabola was now reflected downwards, vertically stretched. We don't have to worry super hard about that, but it's a little narrower after the reflection, and then 1 unit to the right and 5 units up. Once again, emphasizing our vertex is 1, 5. So vertex as a point, 1, 5. Secondly, the axis of symmetry is x equals 1. And lastly, I'll say this on the tablet in just a moment, because our parabola opens downwards, our extreme value is a maximum. We have a maximum value of 5. And before I switch it over, what that means is this y coordinate, 5, is the biggest y coordinate. This y coordinate is 4, this is 2, these are zeros, and so on. Everybody else is smaller. So we have a maximum value of 5. So I'll just kind of say this over here. A is -3. We're going to the right 1, up 5. Therefore, our vertex is 1, 5. Our axis of symmetry is x equals 1. And our maximum is 5. You will be asked to not just say the extreme value, but it's like a drop-down menu. Is it a max or a min? So little side note, even though I've said it, if your parabola opens up, memorize less. That's the smallest y coordinate. Every other y coordinate is up. So just do what it is. This is called a minimum. But there is a little trick, some students will say, well, that definitely looks like a valley. Whereas if your parabola opens downwards, then this looks kind of like a hill, a mountaintop, whatever. Mountain would be a little pointier, but a hill. And so when you're on the top of a hill, you're at a maximum height. So kind of little trick to remember that. And then I always put these little pictures in. Happy parabola, plus opens upwards, sad parabola, opening downwards. This means if your A value is positive, so A is +1, opens upwards. A value is negative, opens downwards. And you can quickly tell whether or not you have a max or a min value just by looking at the value of A. How we doing? Cool. 2 objectives done. Completing the square to solve equations just in general. Completing the square to turn standard form into vertex. It's the formal way of doing it. About 20 minutes ago, I did mention there was a shortcut, and this is it. You don't have to write this all down. I'll tell you what to write down. If we had more time and I could teach the math that you probably don't want to see, or maybe you do, like literally not an hour, 40 minutes, twice a week for 15 weeks, I would take the time and just let us digest and actually complete the square with no numbers. But what I just showed in example 2 with the -3, we would just do with these symbols, right? But it can be abstract because it seems like with numbers, our brains are a little better at tackling them with just letters. But hear me out. We could do that. We call this y, subtract c, divide by a, complete the square. And we would ultimately end up in a vertex form with no numbers. And we would look inside the group like we've been doing earlier. And we know that this really becomes your axis symmetry. Well, let me be a little more careful. The opposite of this. The opposite of +4 is -4. That becomes our axis symmetry. The opposite of -1 became our axis symmetry. So here's the shortcut. If you have standard form, the long road, and that we had to go over, was to complete the square. But a shortcut is to know this fact, that the axis symmetry, and this is something you want to write down, can be found by taking the opposite of B and dividing it by 2A. We're going to confirm that. We're going to go back to the 2 examples we did the long method, the long road with, and just show that this formula works. Ready? What's the opposite of 8? -8. What's 2 times A? 2. What's -8 divided by 2A? -4. It worked. What's the opposite of +6? -6. What's 2 times A? -6. What's B, or the opposite of B, divided by 2A? -6 divided by -6? +1. Our axis of symmetry. That's cool. That's much shorter. Told you there was a shortcut coming. But it's important to understand where these shortcuts come from. And for the last time, it's if we formally did completing the square with A, B, and C's, not numbers, we would have arrived at that conclusion. Definitely a time saver and an important formula to know. Would not be given to you on any assessments, so highlight that as needed. True or false, we're going to build off of that. The y-coordinate of the vertex is f evaluated at 9. That's a weird question. The y-coordinate of the vertex is f evaluated at 9. Well, this question is asking about vertex. It's not in AHK form. It's not in vertex form. It's in standard form. Let me use the time saver. Let me find the vertex. So the axis of symmetry is opposite of b over 2a, which is positive 36 on top of 4, which is 9. Is this the y coordinate? No. The axis of symmetry goes through the x of the vertex. Right? Here's the vertex, here's the axis of symmetry. It's not the y coordinate. So how do I get the y coordinate? Oh, if I have an equation, which I do, and I have an x, which I do, I can just substitute it in. Oh, that means true. To find the y coordinate, I would have to substitute 9. I'd have to evaluate the function. So just for the heck of it, even though this wasn't asked on the question, what is the y coordinate? I have no idea. Turn to my trusty calculator. 2 times, I can do this in my head. 9 squared is 81, so 2 times 81. Minus 36 times 9 plus 148, negative 14. So the y coordinate would be negative 14, but the question asks true or false. F of 9 is the y coordinate. The answer is true. Okay. Nice little shortcut there. All right. Next thing I mentioned, that was brief. Objective 3 is called the quadratic formula. Algebra, college algebra, high school algebra. Algebra is a prerequisite for this course. You had to have used the quadratic formula prior to this course. Maybe it was a long time ago. Maybe you had a terrible teacher, but those are all just in the past. This is the quadratic formula, which states the solutions to standard form. Objective 1 tonight was take standard form, complete the square, and solve the equation. Well, now this is almost a shortcut to objective number 1. Instead of doing this path, which wasn't too painful, I could instead have used the quadratic formula for this, 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 and this. And that's the story I'm trying to tell. Completing the square is the proof. If you've heard that word in geometry, you prove things, excuse me. Well, completing the square is the proof of y negative b over 2a gives you the x of the vertex. And completing the square is the proof of the quadratic formula. Do need to know negative b over 2a gives you the axis of symmetry, but this formula is something I do give on assessment, so you do not need to study the entire quadratic formula. Furthermore, if you look very carefully, you will find right there is your axis of symmetry formula. So a little shortcut. Since I'm going to give you this formula, maybe you just remember this part of it is the axis of symmetry. Little study tip for you. I can't go without saying this. There is one fundamental, important aspect of this formula. It says, in order to apply it, you have to have standard form set equal to 0. So I'm going to detour for a minute off my plan, but that's okay. X squared plus 6x equals 7, an equation we did earlier. Is it equal to 0? No. But about 2 minutes ago, I said we could use the quadratic formula. I wasn't lying to you, but we can't quite use it in that form. X squared plus 6x equals 7. Set one side equal to 0. Oh, we can do that. Subtract 7 from both sides. X squared plus 6x minus 7 equals 0. And then the formula says take x equals opposite of b plus minus b squared minus 4ac, all divided by 2a. So we get negative 6 plus and minus the square root of 6 squared minus 4 times 1 times negative 7 all over 2 times 1. Make 0, A, B, C. Don't have to memorize that formula. Substitute in the values. And number crunch in your head or number crunch with a calculator. Again, I suggested this particular calculator for a variety of reasons. I'm going to type in the fraction because there's a fraction on my tablet. Negative 6. Now, there's no plus and minus, so I just have to do one followed by the other. So I'll start with plus square root of 6 squared minus 4 times 1 times negative 7, all divided by 2 times 1. And just like that, I don't have to go crazy. I like this calculator because it can handle exactly what's on your paper. Calculator you have might not. Happy to look at it after class, but this one will. So taking the plus route, 1. Taking the minus route. Oh, you didn't see that. Another thing that you can do with this calculator is cursor using the keypad up to your formula. Clicking enter copies and pastes it. Then I can use the keypad again just to switch over to that plus sign in front, change it to a minus, and simply hit enter, and I get my second solution pretty quickly. I do not work for TI, but I would recommend this calculator if you haven't. I can't remember all the things we do in trigonometry, but this is the calculator I'll be using. It's a calculator I suggest. And this idea of copy and paste will be helpful with future formulas to come in trigonometry and beyond. I'll let that conversation go. Back to the concept here, be able to apply the quadratic formula. No, you don't need to know memorize it. You do need to know it, just recognize it. But you don't have to memorize it. Said that a few times. And again, just summarizing everything that's happened thus far tonight, completing the square is a skill. You need to know how to do it. Future concepts rely on it. However, specific to quadratics, there are a shortcut for two main things we need to do. One is think graphically. Okay, if I don't have vertex form, the long road is complete the square, but there is a shortcut. Take negative b over 2a. That gives you the x coordinate of the vertex. And actually, the reason I put this question here was to emphasize to find the y coordinate, you substitute it in. Now you have your vertex in a completely different way. Similarly, solving equations, you can complete the square on standard form. However, you can also use the quadratic formula. And just to emphasize, the two numbers we got were the same two values we found earlier tonight. Both 1 and -7 right there. Right. And actually, at this point in the class, it's good to kind of recognize we have a third way for solving quadratics that you did on the exam, which I'll pass back on Wednesday, called factoring. So you got to take the quadratic and factor it. Check mark. We've now discussed in this course the 3 ways to solve quadratic equations. 4 ways. Square root property with completing the square, factoring, quadratic formula. So square root property, completing the square, either counts as 3 or 4, but 3 methods. Let's look at one final example before we smack some applications down. Just kind of straightforward. Here is a quadratic written in standard form. We need to find a lot of its key features called axis of symmetry, vertex, domain, range, maximum and min value, and all the intercepts. Give the intercepts in both exact form and decimal form to 4 places. And then finally, we will sketch its graph. So just giving you a minute to copy this all down. I see the pencils moving furiously. One part of this is done. Axis of symmetry, know the formula, negative b over 2a. B is 12, make it negative. And if it was negative, you make it positive. Divide by 2 times a, 2 times 1 is 2. Negative 12 divided by 2, negative 6. So nice and clean, x equals negative 6. That true or false question was intentional. You find the y coordinate by substituting in your axis of symmetry value. So 2, vertex. The way to think about it is we know negative 6, we need its output. So f of negative 6. I can do this in my head. That's 36 plus 12 times negative 6. I'll use a calculator because I'm good at making number mistakes. 36 plus 12 times negative 6 plus 31 is negative 5. Your vertex is a turning point, so it must have an x and a y inside parentheses. I'm going to purposely skip domain and range for a moment. Although I could do it, I just want to skip it. Let's talk about the extreme value, max or min. Well, our a value is positive. That's happy. Smile. Upward. So smiling, that means our vertex is y coordinate is a minimum. So 3. A is greater than 0. It's another way of saying positive, which means our vertex opens up, which means minimum. That's going to be our smallest y value. Now I'll talk about domain and range. The domain for a quadratic function is all real numbers, just like it is for lines. Fact to know. Unless there was some silly restriction, I don't think we have to worry about that in this course. You should absolutely know lines, mx plus b, and now quadratics have a domain of all real numbers. Fact. Must know for calculus. The range is pretty much spelt right for us. We have a ranges y values. This is the smallest, the minimum y value. There's nothing smaller. Your range is bracket -5 comma infinity. There can't be a smaller y value. There can be greater ones as high as you want to go, but there is no smaller y value. How would that change if we had a maximum? The y is a maximum, and you'd put your maximum right here, and there'd be no minimum. It'd be -infinity comma your max. Find all intercepts. Okay. To find the y-intercept for any function in the world, you sub in a number. What number do we sub in? What number? 0. Always. When we get to trigonometry, find the intercept for this sine, cosine graph. You sub in 0. mx plus b, sub in 0. You output b. Maybe that made a, whatever. Always sub in 0 to find the y-intercept. I think I can do that in my head. 0 squared, 0. 12 times 0, 0. Love finding the y-intercept. 31. Or as an ordered pair, you could say 0, 31. Either of these. If it just says, what's the y-intercept value, then you just give the value. If it says, what's the y-intercept as a point, you give the x is 0 and the y is 31. Just pay attention to what MyLab says, because MyLab can be fussy about how it wants its answers. But mathematics is bigger than MyLab. Mathematics says to find the y-intercept, you sub in 0. And we know it's at 31. So,
Can we just say that C equals the y-intercept?
Yep. Only in standard form, absolutely. Find the x-intercepts. We do sub in a number. We sub in 0. But for the output, that's different. This says, give the function 0 and let it eat it up. This says, change the y coordinate to 0. And now we have an equation to solve for, which we'll use the quadratic formula. We could try factoring. What are the factor pairs of 31 that add to the middle? 1 and 31, and that's it. So since it does not factor, use the quadratic formula. already showed. What to do from here? Turn to your trusty calculator. And because I know a few of us have this one or something like it, you might get an answer that looks like this. The square root of 5 not inside the square root is a -6. That's our exact answer. I'm just going to structure it in a moment, once I switch back to the tablet, as -6 in front and then plus a square root of 5. You'll see it in just a minute. Now, cursor up, enter, or retype, but I like to copy and paste. Change this to a minus. And now I have a -5 with a -6. So negative root 5 minus 6. And on paper, there's your plus and minus. Plus square root of 5, minus square root of 5. So from earlier tonight, I said I structure it very properly. Put the number here, and then your plus and minus number second. So really, it's -6 plus and minus root 5. And that's your exact answer. To approximate, change it to a decimal on your calculator. -8.2361 after rounding. And -3.7639 after rounding to 4 decimal places. Actually, that didn't round. This one rounded up. Those are your approximate x-intercepts. All right. Last but not least, sketch a graph of all this jazz. The way to do that is to utilize symmetry. Absolutely utilize symmetry. Parabolas are symmetrical about their axis of symmetry. So let's plot our vertex for sure. -1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. You can just sketch that in your notes. You can maybe mark it as -6, 5. -5, my bad. Plot your vertex. And now, as many points as someone asks you for. Usually on a test or quiz, I say 5 total points, one of which being the vertex. But that really only requires you doing 2 more pieces of work, because I'm going to utilize symmetry. The next piece of information I'm going to substitute in is this x value, which is what? If this is x is -6, what's this one? -5. I go to the function, I input -5. I can do the first one in my head. -5 squared is 25 plus 12 times -5 plus 31 outputs -4. So I plot that point. 1, 2, 3, 4. And I'm going to utilize symmetry, which this is in my way. There's 1 on that side. Symmetry. I'm going to substitute in one more number, not -6. That's where the vertex lies, not -5. I just did that. I'm going to choose -4. Again, substituting it in makes +16 plus 12 times -4 plus 31 outputs -1. -4 is my x, -1 is my y. and utilize symmetry. Connect this with a smooth curve. And in MATLAB, you can just tap the graph to get the points, or you can type in the coordinates. There is a magnifying glass that allows you to zoom in on the picture. I encourage you to use that. You don't have to if you have great eyes, but I found it helpful.
I was having a hard time being able to type in the coordinates.
I can look at it with you.
Maybe I was missing something.
Yeah. And let's just see, does all of this seem reasonable? I mean, the best way to do that is check on Desmos, but here's some quick checks. A value is 1. So again, I have a happy parabola. I have an opening up parabola. Yes, I do. I found my y-intercepts as 31. Yeah, that's probably going to hit there at some point, way up in 31. So again, am I 100% sure my work? I'd be nervous if I had a y-intercept of -2, I'll tell you that, because then they wouldn't be in agreement. So the fact that this is 31 and that's nowhere near the y-intercept, I feel like that's an agreement. If I check out the x-intercepts, -3.7 and about -8, -1, 2, -3. Yeah, I mean, I sketched it from that point, but yeah, that definitely seems reasonable. It's -3.7, I guess. And it's this guy over here about -8 something. So that's -4, -5, -6, -7, -8 and some. Yeah. So I'm arguing this does seem pretty reasonable, and I'm confident that it is correct, right? So taking a standard form, quadratic function, and then finding all these key pieces, check mark. Last objective for tonight is to look at some applications. How are quadratics used? Definitely in the study of projectile motion in science. It was some guy, I think he's kind of famous, maybe not, Isaac Newton, and another guy, Galileo, who ran experiments. It was Galileo actually went to the Leaning Tower of Pisa because of its tilt and dropped objects because he knew its height. And he had observers and people measure time at different heights. And you can research any more of the story that you want to. I wasn't there personally, but so I've been told. And I've researched it. It's a little fascinating. But it was through Galileo's experiment and Newton's story of watching an apple at rest falling down to earth, these idea of gravity and then thinking about what's going on here, yada, yada, yada. But through experiments and measurements, they established that things on earth fall, and there's a lot more to this, but I'm trying to keep it short and simple and at least somewhat engaging, in a pattern that forms a quadratic function. Interesting. And so through their experiments and many other scholars they work with, and years past, it's been formally established and proven that projectile motion, things that are either projected like a firework or out of a cannon, or things that are dropped from the top of a building, fall to earth under a pattern that is a quadratic form in nature. So anyways, a little backstory on that. So one application, obviously, is to look at some scenario that says, all right, here's a function that gives the height of a projectile x units from its release. So something's probably being fired, boom. So the x here will tell you how far. So if you're like, let's just give this a little storytelling. We're here, we're launching t-shirts into a crowd of sharks that are going to eat the t-shirts. And I don't know why, but they are. And so, boom. And if I said, here's 10 feet from us, we could sub in 10 and find how high the t-shirt's in the sky. Kind of cool. Or maybe the NFL is doing this. They're setting their cameras and they have a lot of data about punts and they don't want the football to hit the camera. Might be important to know about how high that's going to be from where they're stationed. Anyways, I can make up stories all day and night. There's our function. I tell a story to understand it better. X is the distance from its launch, and Y is however high it's in the sky. So I'm feeling like it's going to hit the ground. The hungry sharks are going to eventually eat it. Find the maximum height and how far it was released. All day and night, that screams, find the vertex. Part B asks us to find the distance the object hits the ground. All day and night, that sounds like an x-intercept. And lastly, find the initial height. All day and night, that sounds like a y-intercept. So not just finding the key features for a question we did about 5 minutes ago, but now putting it into Galileo and Newton's observations. Here we go. Find the maximum height. Big takeaway from tonight. The axis of symmetry is opposite of B over 2A. Starting to summarize tonight's lesson. Negative 2.7 on top of 2 times negative 0.05. And imagine that works out to be a beautiful number, like it was rigged. It was 27. We're going to substitute in 27. True or false question? True. To find the y coordinate of a vertex, you substitute in the axis of symmetry. Again, summarizing the lesson now. Also summarizing, you need a calculator. I don't have extras, and we'll talk about the test when that comes around, but for your homework, you got to find a calculator, which you can use Desmos calculator for, just the actual calculator part. And this comes out to be 42.05. And that's an exact answer because the decimal terminates. It's literally 2 decimal places that terminate. So that's an exact answer. Now we can answer part A. Find the maximum height. That's the y coordinate. That's this. And how far it was from the launch. That's your x. So at 27 feet from the launching pad, its height was a maximum of 42.05. And I don't think it says feet, so I'm just going to say units. I don't know if it's measured in feet, units, meters, or what. And there is a thorough sentence to kind of complete. Probably could have used a little better English. At 27 units from launch, its height is at a maximum. That's okay. I don't claim to be an English major. Find the distance the object hits the ground. So we need the x-intercept. We're going to take our function. set it equal to 0, and use our good old quadratic formula. Do not need to memorize. Definitely not going to switch over to the thing just for time's sake. Negative 2.7. Again, make sure you use your fraction bar if you have this calculator. It's a lifesaver. And when I did the plus, I got a negative 2. Now I have to do the minus. Copy and paste. Get all my review and all my summary at one point. And I get 56 with the minus. Only one of those answers seems reasonable, though. And the picture of the context, the story, tells a full story. Because a parabola actually goes on forever. I said its domain is all real numbers. But in the context of this situation, it really only makes sense to talk about this. Right? The fact that I'm getting negative 2 does not make sense in this context. That doesn't apply in this diagram at all. Yeah, it's an x-intercept for the sake of being an x-intercept, but there's no such thing as negative. Well, maybe there is, but I don't want to open that can of worms. Like we launch and all of a sudden it's like, whoops, we got to fix that. The sharks are still hungry over there. No, all right. So we're not going to include this negative value. We're talking about the time it went or the distance forwards. So I don't want to say it's an extraneous solution. It's just not applicable in this situation. 56 is the only answer. And I end with this. What is the initial height of the object? The y-intercept is as simple as subbing in 0, which I don't need a calculator for, 5.6. At 5.6, again, I should have put feet or meters on this. I apologize, I didn't. It's not important to this. The big idea is you sub in 0 to find that initial launching height. The homework is live. I did not get to the remaining applications. You may have seen them in a previous algebra course, but I'm amending the homework right now to get as much of it done because there is more to come on Wednesday. We'll pick up right from here and into polynomials. So strongly encourage, I know there's 31 questions, about 10 of them are just vocab words. So again, I think 31's a lot to assign. So this is why I'm almost saying I don't feel bad because the first 10-ish are just like, hey, if a parabola opens and you check up or down, if a parabola opens up, then it has a maximum. So you got to make sure you choose the right up or down and things like that. And then there's a few you got to actually execute the stuff for. So see you guys on Wednesday. I'll have your test and all that stuff.